Welcome back. In continuation with the last session, in this session we will be discussing about the various types of condensers used in a refrigeration system. So once the refrigerant gets compressed in the compressor, it will be given to supply to the condenser where the heat rejection will be taking place. The heat absorbed in the evaporator in a refrigeration system will be rejected at high pressure in the condenser. Actually, in the condenser, there will be a phase change process taking place. The vapor refrigerant will be transformed into liquid refrigerant by rejecting its latent heat. So, these are the functions of a condenser to transfer heat from the refrigerant to the medium, such as water or air. By rejecting heat, the gaseous refrigerant, the vapor refrigerant will be converting into liquid or condenses to liquid. So heat rejection is taking place in the condenser. So you might have seen the condenser tubes in your household refrigerators. Nowadays it is sealed, the rear side of the refrigerant. In older days, you might have seen the black zigzag, the horizontal and vertical tubes placed behind the household refrigerators. These are the condenser tubes. You can feel the warmth near that those tubes where the heat rejection is taking place. So that's why usually in a refrigerator manual, it is noted that you should keep at least some 10 to 15 centimeter distance from the wall so that efficient heat rejection will be taking place. There will be a movement of air. So usually air cooled condensers are used in a household refrigerator. So coming to the types of condensers, there are water cooled, air cooled and evaporative type condensers. In water cooled condensers, depending on the type of heat exchange taking place, there could be shell and tube, shell and coil and double tube or tube in tube condensers depending on the type of heat exchanger employed in the condenser. Now coming to the air cooled condensers, the air could be forced with the help of a blower or fan so that efficient heat transfer is taking place, or otherwise natural convection. So just the hot air will be going up and the cool air always will be at the bottom side. So air cooled condensers could be forced convection or free or natural convection type. Then the third category is evaporative condensers. So this is the schematic representation of a water cooled condenser. So you can see here. So you can see here the two types of water cooled condensers. So this is open shell and tube. So where inside there are tubes, you can see the cut section here. Inside the tubes, refrigerant will be flowing. Okay, and water will be cold water will be sprayed over those tubes in which refrigerant is flowing. So what will happen? The hot refrigerant will get condensed by transferring heat to the water, and the hot water will be coming out through the valve. And coming to the double tube heat exchanger, you can see there is a tube. This black color is a tube, and outside there is another tube. So one tube is placed inside another tube. So the inner tube is containing refrigerant, and the outer tube, the annulus of the inner tube, containing water. So again, the heat transfer will be taking place from the inner tube to the outer tube. So there are different arrangements of the same heat exchanger depending on the situation and the amount of heat transfer requirement. Okay, so these are the first two categories: shell and tube heat exchanger and double pipe heat exchanger. And you can have shell and coil heat exchanger, and so here you can see the shell and tube arrangement with the clear schematic diagram. So water tubes and the shell. This is the line through which so here the arrangement is different. So water is going through the tubes and the refrigerant is powered over the tubes containing water, and the cold refrigerant will be subcooled liquid from the condenser, that is the condensed refrigerant will be flowing out of the condenser. So the inner tubes are carrying water here. So whichever arrangement is better for that particular application, that will be used. So these are the features of shell and tube condensers. The mechanical cleaning is possible. Compressor discharge gas is piped into the shell, that is possible. So water flows through the tubes in the condenser depending on the arrangement again. The ends of the shell are removed for cleaning. So the both ends of the shell, you can see here, this black colored, these are the caps which can be removed so that the entire cleaning is possible. Shell acts as a receiver, receiving the hot energy, thermal energy. At the same time, it is the most expensive. So this is a cross-sectional view of a tube-in-tube condenser. Tube-in-tube heat exchanger type condenser. There is an inner tube and outer tube. The annular space may contain the refrigerant or water depending on the situation warrants. So here in this particular diagram, water from the cooling tower is provided in the inner tube and the hot discharge gas from the compressor is in the annular space. Now another category of condenser is shell and coil condenser, where you can see a coil which carries water and the shell carries the refrigerant. The refrigerant will be powered over the coil and the coil will be receiving the energy from the refrigerant and it will be getting warmed up and discharged from the coil. So these are the features of shell and coil condenser. Coil of tubing enclosed in a welded shell. Water flows through the coil. Refrigerant is discharged into the shell, what we have seen. Okay. So it is, when compared to the other types in shell and tube category, it is more efficient than air cooled condensers. So water temperature could be maintained easily. Water temperature directly affects system pressures. So that is water cooled condensers. Now coming to the air cooled condensers, you can see there is no secondary liquid required, rather air is used to, the cool air passing over the condenser tubes is used to condense the refrigerant. So you can see the condenser tubes are mounted on a plate. Okay, so air will be flowing over the tubes. So bottom cool air will be rising up when it's getting heated up. When the air gets heated up, because of the density difference, the air flows up. The hot air will be moving up, and bottom side the hot air will get replenished with the cold air. So it can be of plate type and tube and fin type. Now coming to the last category of condensers, evaporative condensers. Evaporative condensers. So the refrigerant will be coming in here, hot gas inlet. This is a refrigerant in from the compressor, and the condensed liquid refrigerant will be going out from here. So how the condensation happens is, there is a motor. Okay, there is a circulating pump of water. So water will be pumped and splashed over the tubes carrying the refrigerant. So evaporation takes place, evaporation of water. After absorbing heat from the refrigerant flowing through these tubes, water gets evaporated and the moist air will be removed here. You can see here. So this could be used in industrial refrigeration systems where large amount of refrigerant flow rate is there, large quantity of heat is to be removed. In such arrangements, we may have to employ evaporative condenser. So this is a more clear arrangement you can see here. The refrigerant is flowing through this tube and water is sprayed over to it using suitable nozzles or showers, and the water vapor will be escaped out. Moisture air will be escaped out through this after drift eliminator, and the used water will be collected here in the water sump, and the same water will be pumped again using the water pump. Now coming to the little analysis of the condensers. So if you look at the pH diagram of the vapor combustion refrigeration system, 2 to 3 is the process of condensation. So the heat transfer in the condenser, that is the heat rejected in the condenser, is given by m dot into H2 minus H3. M dot is the mass flow rate of the refrigerant. H2 and H3 are the inlet and outlet specific enthalpies of the refrigerant in the condenser. So required condenser area could be evaluated using the heat transfer expression UA delta Tm. Delta Tm is the mean temperature difference between the refrigerant and external fluid, which could be air or water. So U is the overall heat transfer coefficient, A is the area required for the condensation to take place. Now there is another important terminology associated with the condenser heat transfer analysis known as HRR, heat rejection ratio. Condenser heat rejection ratio. So that is given by the ratio of heat rejected to the heat absorbed. Also, this is the loading on the compressor per unit of refrigeration. So QC by QE. So what is QC? It is the heat rejected from the refrigerant in the condenser. C stands for condenser, E stands for evaporator. Okay. So QE is the heat absorbed in the evaporator. QC is the heat rejected in the condenser. So the ratio of heat rejected to the heat absorbed is termed as heat rejection ratio. So QC is equivalent to, as per thermodynamic principles, QE plus WC. WC is the compressor work required to pressurize the vapor refrigerant, or it could be written as 1 plus 1 by COP. So heat rejection ratio of a condenser is given by 1 by COP plus 1. Okay, this is very important. Please keep a note of this. So at a given evaporator and condenser temperatures, the heat rejection ratio of condenser in refrigeration systems using hermetic compressors. So we have seen what are hermetic compressors are in the last session. So when hermetically sealed compressors are used, the heat rejection ratio is higher than that of open type compressors for the given temperatures of evaporator and condenser. So this is a summary of today's session. The condenser is a system component responsible for rejecting the system heat. So they reject both latent as well as sensible heat, so that complete conversion of vapor to liquid of refrigerant take place. Water cooled condensers are more efficient than air cooled condensers. More effective heat transfer is taking place. So there are three types of water cooled condensers: tube in tube, shell and coil, and shell and tube. Then mineral deposits in the water circuit reduce the heat transfer rate, as you have studied in the heat transfer in detail, the fouling in heat transfer. So that fouling reduces the heat transfer rate. If you have any questions or any doubts to be clarified, please use the comment section below for your comments and valuable feedback. Thank you.